Okay. So first, thank you very much for being here today at 9 a.m. And obviously, thank you very much, Albert, for your invitation. So I'm super happy, to be with you today at the SMAI-SIGMA Day, because I only have fond memories of SMAI-SIGMA, obviously, at Curves and Surfaces and Arcachon and everything. And, my understanding is that with those talks, we're meant to introduce ourselves to the community. So as a very quick CV, I was trained as a mathematician in Paris. Then I did my PhD in SACLE on medical image analysis, like image registration, these kind of things. Then I spent the COVID years in London studying geometric deep learning and working on protein-protein interactions. And since 2021, basically I work as a permanent researcher at Inria Paris in the HeKA team. And what is a HeKA team? Well, it's a truly translational research team for public health. So that's a very healthy interdisciplinary mix of medical doctors, pharmacologists, Inria researchers, INSERM researchers, like experts on clinical trials, those kind of things, and people from the Université Paris Cité, both professors and engineers. And so my main motivation really is always to develop robust and efficient software that stimulates other researchers. I really want to provide useful building blocks that people can then take and make great research with. So among the things that I work on, maybe the most important one, that I worked on with Joanne, who is in the room, etc., is really everything that's related to speeding up geometric machine learning and geometric computations more generally on GPUs. So I'm one of the main contributors and maintainers of the PyKiops library that we'll quickly talk about during the talk, which is basically an extension for PyTorch, NumPy, R, that enables really very fast speed up for all the computations that are related to distance and kernel matrices. So it's something that has been already downloaded like 500,000 times, very useful. So you can have a look, if distance transform means something to you, or kernel matrices, probably have a look. Then I also work especially, to integrate in my team to scale up pharmacovigilance, like survival analysis, to the full French population. Because I don't know if you're aware of it, but as an Inria researcher now, basically I have access to a pseudonymized data set that contains all the carte vitale information for the 70 million French people. And basically the key now is to see if we can detect very suspect correlations between, I don't know, some kind of contraception method and then breast cancer, these kind of things. And basically to do this in a way that's going to be accepted by the public health community, you have to take the statistical packages that they know, especially the R survival package, which is by far the most important package for clinical trials, and scale it up to 70 million people. Basically, how do you go from a clinical trial cohort, 10,000 persons, to 10 million people? And so I've worked on it for 2 years now, and basically we have re-implemented it with full backward compatibility on the GPU, so 100 to 1,000 times faster, and it's called Survival GPU. And then finally, because I love doing 3D stuff, I want to ease access to modern statistical shape analysis. So I worked a lot on optimal transport theory with the Geomlos library that I'm going to present today. And now for about a year now, I've been working on a scikit shapes project with a great engineer who's called Louis Pujol. And so it's going to be released pretty soon. Okay, but no spoiler today. Okay, so today's talk, it was really designed assuming that you would enjoy some applied math, so not the pharmacovigilance stuff. So I decided first to introduce, in case you don't know it very well, the optimal transport problem, then talk about efficient discrete solvers, and finally, show you some applications, open problems, the kind of thing that I work on, and obviously just as a start for the discussion. So first, what is optimal transport, if you've never seen it? Well, the way I like to introduce it is to say that optimal transport is what generalizes sorting to spaces of dimension d larger than 1. So how do you sort points beyond the real line? Okay, so let me consider the most simple case, 2-point clouds, A, that I'm going to denote x1, x2, x3, x5, xn, and B, y1, y2, y3, yn, 2-point clouds in RD. So then we can define the optimal transport problem between A and B as the minimum of this quantity. So that's what you call the Wasserstein squared distance. But so basically it reads like a squared Euclidean norm. You just take the average of the xi minus yi squared, where those norms are just norms in RD, with a twist, which is that I try to minimize over all possible labelings of the yj's. Okay, so basically optimal transport means that the optimal transport distance means that you take just a squared Euclidean distance up to permutations. And the kind of unexpected benefit from it is that this optimization problem allows you to define what it means to be an increasing mapping, what it means to sort the point yj's with the xi's beyond the real line. Because let's assume that my 2-point clouds were on the real line. Okay, so I have x1, x2, x3, x4, x5, and then the target points y3, y5, y2, y4, y1. Well, it's not very hard to show that the optimal labeling between those 2-point clouds is the one that is going to match x1 with y3, x2 with y5, x5 with y1. Okay, and why is that so? Because assume that you had a kind of non-increasing transposition in your permutation, basically a crossing. Assume, for instance, that x4 was matched with y2 and x3 was matched with y4. Then basically, due to the fact that the squared Euclidean distance is strictly convex, you would just show that it's always in your best interest to permute this. And so that's how you show that even though you haven't used the ordering structure on the real line, just using the squared distance, you have retrieved this notion of an increasing map. And actually, you can show that optimal transport is going to retrieve the unique gradient of a convex function that maps your two distributions together. So going further, it's pretty easy to generalize this to point clouds that don't have the same number of points, maybe weighted points, even continuous distributions. And to do this, basically, we'll recast this optimization problem on permutations into a linear optimization problem on matrices, basically permutation matrices P. So the definition of optimal transport that I'm going to use throughout the talk is this one, and it's equivalent to the first one, but OT between the two distribution A and B is that I minimize over all the n by n matrices. So you can think it's like a general plan. At coefficient ij, you have how much mass should go from point xi to point yj. You minimize this cost, which is linear with respect to the Pij, and basically you have constraints that force your transport plan to be a permutation matrix. Okay, so your constraint means that Pij should be non-negative, and that each source point should be transported onto the target. And we'll see a few other illustrations later. So practical use, alternatively, you have other interpretations of optimal transport. Maybe the one that I prefer, because I work with 3D things, is that optimal transport, it's really nearest neighbor projection with an incompressibility constraint. Okay, because if I take this problem and that I optimize over all applications sigma from 1n to 1n, basically what you would retrieve is just the points would be matched onto their nearest neighbors. And the thing that I do when I add this constraint that they should be permutations is that I ask my points to spread out. Basically I don't want x1, x2, x3, x4 to all be mapped onto y3. They have to move a bit in the chaise musicale game. Okay. Otherwise, you can say that it's just a fundamental example of linear optimization over this transport plan variable Pij. And in practice, this theory induces two main quantities that you can use for applications. First, you recover this transport plan Pij, or equivalently, this optimal mapping from xi to y sigma I. So that's pretty useful. That's your nearest neighbor projection. Or you can just use this Wasserstein distance, like the square root of OT of AB, as a well-defined distance between probability distributions. So before going any further, because it has a fancy name, optimal transport, I just want to make it clear how this object behaves on simple examples. So here, my source distributions, the points x1, x2, xn, I color them using a rainbow color scheme. And my target points, my target distributions, it's like this saxophone. Okay, so I map a potato onto a saxophone, and basically this is what the result looks like. Okay, this is at the start, and here you have sent the point xi onto the target x y sigma I, and you retrieve this. Okay, so the first thing that you remark is that okay, you get this kind of bijective covering, this bijective pairing between your 2-point clouds. It's kind of smooth most of the time, but it's not smooth. Okay, like if you see colors, I hope so. Otherwise, sorry. Basically, here you have this red, the yolk of the egg, got split up here between there and there. Okay, so going forward, you can use it if you want to map a potato to anything, to a crescent. And in machine learning, people sometimes like to do that for generative modeling. Okay, so you can do that. For me, in shape analysis, I'm more interested in mapping shapes. Like this really looks like the slice of a kneecap, for instance. Shapes that are kind of close to each other. I'd like to get pixel perfect matching very quickly. And if the shapes are close enough, okay, basically this gets mapped there, this gets mapped there. You have distortion because it's a very cheap mathematical optimization thing. It's not, it's not an expensive physical model, but it's a start. And to be clear, I think that this is worst case scenario for optimal transport. So whenever you think about optimal transport, think about this counter example. Okay, so here, this is my source distribution, first moon, and this is my target distribution. And ideally, I think you'd like the ends of your distributions to be mapped together. Mm-hmm. But if you look at the color scheme, this is not at all what happens. Okay, optimal transport, it's closer to sorting than it is to diffeomorphic registration or things like that. Okay, so for instance here, basically because the dominant axis in this configuration is the x-axis, if you look at what happens, this part there doesn't get mapped there, it gets mapped there, okay, here. So basically here, you see a reordering of the points along the x-axis. So my advice would be not to trust too much optimal transport if your distributions are too far away from each other, but okay, for something that's supposed to be cheap, very easy to study, it's already a good start. So it's worth studying. Personally, yeah.
It's a weighted version of your first line, what you consider here.
It's a weighted version?
A weighted version, and you consider distributions. Or not
yes. So here, because it's simple slides, it's just 10,000 points drawn uniformly on a PNG image that I showed. So here it's actually a bijective mapping because I have 10,000 points. Oh yeah, it's just a color identifier for each point. Yes, yeah. Sorry. Okay, sorry. Yes. Oh, sorry. I hadn't. Okay, no. I mean, that's the problem with images. You always assume that people see them through your eyes, but no. Here, just to see who goes where. In computer graphics, people like to have those checkerboard textures. It's exactly the same thing. Okay. Now, maybe for me, and probably for you, the main motivation to study optimal transport is that it induces a very canonical geometry-aware distance between probability distributions that lifts your distance between your samples to the space, for instance, of Gaussian distributions. So let us look at maybe the most fundamental family of probability distributions, which is the family of Gaussian distributions in 1D, the normal distributions. So, this symbol n that we like to teach to our students, you can say it's an application. It's not just a notation, it's an application that takes as input a mean value on the real line and a standard deviation, which is non-negative, and assigns a probability distribution n of mean m and standard deviation sigma. Okay, now so you can say it defines a statistical manifold. So you have a 2D upper plane and you embed it into the space of probability distributions. And now the question that you ask yourselves is, okay, given all the different distances, divergences that you can define between probability distributions, if I endo the space P of R, the space of probability distribution with a given metric, what is a pullback geometry on the space of parameters? Like how is it reflected on the hyperplane? And then what's very interesting is that two of the most canonical distances or divergences on the space of probability distributions give you, through this very canonical Gauss map, the two most canonical and invariant distances on the upper half plane. Why is that so? So maybe the most fundamental distances between probability distributions, or pseudo distance, is the relative entropy. You know, the Kullback-Leibler divergence, and infinitesimally, it's called the Fisher-Rao metric. And if you do the math, it's just a simple calculation. I give it to students in my lesson. You realize that basically the Fisher-Rao metric on P of R induces the Poincaré hyperbolic metric on the upper half plane. So that's very remarkable. And what does it mean in practice? Okay, it means that as far as the relative entropy is concerned, the geodesics is the shortest path between a very peaky distribution there, you know, a very peaky distribution on the left, and a very peaky less peaky distribution on the right, you know, is going to go through a very low confidence state. So just to be clear, because this very peaky distribution here, it's this mean and a small sigma. This corresponds to this mean and a medium-sized sigma. And then if you know a little bit about the Poincaré hyperbolic metric, geodesics, you know, are those half circles. So basically, to go from there to there, you go through a very high temperature, low confidence state. You know, and the way I like to say, you know, it's kind of relevant because think that the real line is the space of political opinion, the spectrum of political opinions. And you say, okay, maybe, you know, this is an 18-year-old, he's hardcore left-wing, so very, very, very confident that he wants to vote for Mélenchon at the next elections. And this is maybe the same person, age 60, so I don't know who will be the right-wing candidate in 40 years. You know, what is the most likely trajectory? Is it that the person went from, you know, hardcore Mélenchonist to then, okay, socialist, then Macronist, etc.? Not really, you know. It's kind of more likely that people kind of first lost their beliefs, their ideals, and then selected something else. You know, I'm not a political scientist. I don't know how relevant this is for political opinions, but it's a great way of remembering it. But at the very least, you know, it's something that it's a very good default baseline when you don't really know about the structure of your sample space. So for instance, it's extremely popular in machine learning, for instance, to model the evolutions of consumer choices. You know, this is exactly the type of metric that Amazon wants to use to model people's interest, because, you know, maybe at some point I want to buy 3D printing stuff, then I want to buy books on the Roman on my next trip, etc. So, you know, this kind of behavior is useful. It's a very nice thing to study, so, you know, that's information geometry for you. But realistically, you know, if I want to do 3D stuff, that's a bit far-fetched, you know, as a behavior. I would rather have something more linear. I would rather have a linear interpolation in terms of the mean and a linear interpolation in terms of the standard deviation. And guess what? This is exactly what you get when you endo the space of probability distributions with the Wasserstein metric. So for me, it's kind of a very, very strong motivation to study it, because then I can hope to get the same kind of behavior for other types of probability distributions, at least unimodal. So that's it.
Yeah, because you've got this very nice interpretation as a pullback geometry sphere parameter. Now, if you have a specific geometry and the space of parameters that you want to preserve with some particular geodesics, is there a way to define a good related optimal transport like distance in the space of probability? Or?
I don't really know. It's typically the kind of open problems that you can think about. No. I don't know. Yeah. So now that you have your motivation, how should we actually solve the optimal transport problem? So to start to get tractable algorithms, you need this fundamental insight of duality, you know, which was kind of formalized by Leonid Kantorovich during World War II, you know, and so I don't know the story, but basically he's one of the only Soviet person who got a pseudo-Nobel Prize for economics because of this. And basically Leonid Kantorovich understood that in very concrete sense, central planning with n times m variables, so a quadratic memory footprint, is equivalent to outsourcing with n plus m variables, so a linear memory footprint. So that's very, very important. So I spent a few minutes on those slides. Okay, so let's look at the optimal transport problem as I defined it for you. So at least in the second form. So here I have my two discrete distributions. The first one, A, is defined with 4 weighted direct masses. One direct with weight alpha 1 at location x1, weight alpha 2, location x2, etc. So 4 points. And here, basically 6 target locations. Historically, it was really like where do we produce wheat and weapons, and where should we send them on the front? That was extremely concrete. And basically what you want to do is to optimize on a 4x6 general plan. You want to say, okay, how should I allocate my trains, to take wheat and shells from Novosibirsk to Stalingrad? Okay, like you have this map, you want to optimize on it, and so you want to find the map first, which actually transports your wheat and weapons from the source cities, from the source locations to the targets. So your transport plan, you should have positive weights, no negative weights, because it doesn't mean anything to transport negative weights. And basically, you want to make sure that if you sum row-wise on your transportation plan, you get the actual production at the given city. And when you sum column-wise, you should get the actual requirement, of these very specific cities. So you have those constraints, and then you want to find the plan that satisfies those constraints, which induces a minimal cost. So the minimum, if you sum over all the trains, and you have the cost of a train. So here I say just like maybe 1/2 of the square distance between xi and yj. I want to minimize this, which is linear with respect to pi. Okay, so in a very real sense, that's something that naively you're going to optimize by having this big 4x6 array. And yeah, it's central planning. And the big problem with this approach is that it's never going to scale. Okay, because I want to work with 3D shapes, and M are like on millions of points, at least 100,000 points if you want to represent a brain surface. And no one has enough memory, to store in memory a big 1 million by 1 million array. So the first remark you have to do is that this problem, you can formulate a kind of equivalent problem, which is a problem of a postman, of FedEx. Okay, how would FedEx understand this problem? Well, FedEx would say, okay, maybe the system that we can put in place is that I can open post offices in the source and the target cities. And in each of those cities, basically, to send a parcel that weighs 1 kilogram, it's going to cost you a linear cost with respect to the mass. So maybe if you are at location x1 and you want to send alpha 1 kilograms, it's going to cost you alpha 1 times f1. And then, basically, so the sending cost is going to be the sum of the alpha I fi's. And then you put the same system in place at the arrival. So the cost to retrieve the parcels at location y1 is beta 1 g1 plus beta 2 g2 plus beta 6 g6. And so basically, the profit of FedEx, so the money that FedEx wants to make, is the sum of the alpha I fi's plus the sum of the beta j's gj's. So that's what FedEx wants to optimize. And basically, if you're FedEx and you assume that you can do you abstract the logistics away, what you want to do is the general wants to minimize the cost. FedEx wants to maximize the profit. So FedEx wants to say, how can I assign maximum prices under a very important constraint, which is that for every single pair of city, I should propose a deal which is at least as good as what the general would do by sending someone, with a truck. So basically, what FedEx wants to do is to maximize this quantity under the constraint that for every pair ij, the price f of xi plus the price g of yj, so the price of sending a parcel from xi to yj, is less than c of xi yj. And the fundamental insight from Kantorovich is that those two problems have the exact same solution. Okay. And for us, as computer scientists, people who want to do scalable algorithms, this is super important because this problem you optimize on an n times m table, whereas the second problem, it's also a linear programming problem, but you only have n plus m variables. So you can hope to have a linear memory footprint. But well, that's the memory footprint of your data. You cannot hope for less. Okay, so that's the first remark. So maybe keep in mind, anyway, I should write it down. The actual problem that we want to optimize is minimize sum of alpha I fi plus sum of beta j gj subject to for all ij N5 plus gj is smaller than Cij. So it's kind of here, it's like a linear form, alpha f plus beta j subject to f O plus j smaller than C. Because f is like a column and j it's a row vector. Now, okay. Now I'm showing you slides that I never show usually because I think it's too hard for people, but it's SMAI-SIGMA, I'm sure you're going to understand. Okay, how do you optimize this? Okay, this linear problem with respect to the dual vectors fi and gj's. Well, the first thing you can notice is that, okay, the alpha i's, the beta j's are non-negative. So ideally, you always want to increase prices. Okay, in isolation, if the constraint didn't exist, you would do that. So here, I display in a kind of very schematic, as a diagram. Here that's my dual space where I optimize. So first dual variable fi, second dual variable gj, and the linear form that I want to optimize look like this. So the optimum is somewhere where both fi and gj are large. I want to get a very wide point. And then I have my constraints. Tell me, hey, you know what? If you increase your prices too much, no one is going to buy your service. So the constraints look like this. And then the very naive, greedy algorithm is to say I'm going to start with null prices. Everyone's going to like them. And then I'm going to hike up the prices FIs. And then I'm going to hike up the prices GJs. And I'm going to iterate this. That's kind of in an optimal transport 101 class. That's what we call applying C transforms. But the thing is that, okay, just to be very clear, if you see this and you say, okay, I fix the GJs and I optimize on the FIs, then the maximum price that's going to satisfy this constraint is you take basically FI wants to be smaller than C xi yj minus gj for all j. So you have to take the minimum over j of this quantity. And same for gj, etc. You can try to do this and basically it's garbage. You get stuck immediately. You see this in this diagram. Because basically you're trying to make coordinate ascent on a problem which is like this. So you think you're very clever and it stops. Okay? So maybe the first important life lesson in optimal transport is that you have to take it easy and you're going to get somewhere. So a very important algorithm is like the auction algorithm that you can understand as this naive greedy algorithm with a slackness. So graphically, maybe let's not dive too much into the equations. Graphically, it's, okay, you optimize with respect to f, but you restrain yourself a little bit. So you have this positive parameter epsilon, and you say, I'm stopping at a step before the wall. And so this means that I have some margin. And then when I optimize with respect to g, I actually have room for maneuver. I do this, and then I'm stuck to the wall. I say, okay, I should get some margin epsilon, etc., etc. Okay, and doing this, you can show that you're going to get to a solution which is epsilon close to the optimum, in the sense that the cost that you get after your iterations is going to be basically the optimal cost plus maybe something like epsilon. Yeah.
How do you choose the epsilon?
Yes. So yeah. So no. So we are going to talk about it, but here
to make it there to go down.
Exactly. You see that there's a trade-off because if epsilon is too small, you get very close to the optimal solution, but you make many steps. Whereas if epsilon is large, you converge quickly, you get somewhere quickly, but you're not very precise. Obviously, we're going to use annealing. Okay, that's one of the key ideas. But just the thing with this auction algorithm, it's very, very important, developed in the 80s, you have textbooks on it. for us, as mathematicians, it's a bit uncomfortable because the solution, basically where you get at the end, it's not very well defined. So instead, what we like to do is to say, okay, we are going to basically make the same kind of updates, but we are going to understand them as coordinate ascent updates on a softened on a softened objective, and that's what we call doing entropy regularized optimal transport. Okay, so basically, you have this picture. Auction is you have the real linear program, and you make a kind of HeKA dual ascent optimization. Entropy regularized optimal transport is you soften the optimal transport problem. Basically, you take this linear objective and you add a convex penalty. And then magically, you remark that you have those kind of updates. So it's coordinate descent, so it's going to converge towards the optimum of your concave maximization problem. And the updates, now they look like this. Okay, so instead of having minimum minus epsilon, it's more like you have minus epsilon log sum x of the thing. But it's nearly the same thing, because I don't know if you're aware of it, but especially in machine learning, in many fields, you like to say that log of xa plus xb, yeah, it's basically maximum between a and b. So minus log of x minus a plus x minus b, yeah, it's basically mean between a and b, and then you have this epsilon parameter that controls basically how sharp you are with this kind of approximation. That's the core idea of the Sinkhorn algorithm. And then a very important remark is that usually you will find the Sinkhorn algorithm written like that, okay, coordinate ascent. And immediately you see that it's a bit uncomfortable because you don't like to make those coordinate ascent steps, you don't like to make a choice initially. And also in practice, we like to register, I'm interested in cases where the two distributions are close to each other. So if A and B are close to each other by symmetry, F and G should be close to each other. And then it doesn't strike me as very smart to start by leaving the diagonal. Okay, so instead, probably what you should do, and in practice it's really what you should do, is you should use symmetrized updates. Okay? Because with coordinate ascent, you know that if you update F, you go there. If you update G, you go there. Well, it's a concave optimization problem, so worst case scenario, interpolating between the two is going to be at least as good as the worst of the two. And so you can do that, and by construction, you're going to stay close to the diagonal. It's very much an important trick. Now I have a few remarks to make about this algorithm. The first one is that it's very streamlined. It's you have a very nice decoupling between the implementation stuff and the math, because you have only one key non-trivial operation, which is this weighted distance transform. Okay, for every point I, you want to compute this minus epsilon log sum x of gj minus cxi yj, which we write as this kind of minimum, but softened, of cxi y minus gj, g of I, of y. And basically, from a computational perspective, this is very, very, very similar to a chamfer distance transform, if you're from imaging sciences, or to a convolution with a Gaussian kernel, if you like imaging and blah, blah, blah. So you can implement it really fast, especially with spiky ops. So the main cases to keep in mind is that if C, so if your cost is a closed formula, basically a closed formula that takes like less than 50 arithmetic operations to compute, then a brute force implementation of this, an n by m computation on a GPU with ski-ops, it's going to scale to hundreds of thousands of points in something like 10 milliseconds, because our GPUs are really fast now. Then, okay, you can go further, because if A and B have a low dimensional support, basically you can use a clustering and truncation strategy to get a speed up by an order of magnitude. Okay, like Quentin did that more than 10 years ago. And then, also if A and B are supported on a 2D or 3D grid, and if your cost is a square distance, basically here you have a Gaussian kernel that pops up, and if you're an imaging guru, you know that convolution with a Gaussian kernel, you have this trick where you do it separately and it goes much faster. So it's yet another thing. And as a side note, FFTs do not really work because of numerical accuracy issues, but we could talk about it. So remark 2 that we've already talked about is that annealing totally works, you have to use it, okay? For the action algorithm, it's rigorous. For Sinkhorn, it's a bit softer, let's say. But basically, since you improve the dual cost by at least epsilon at each step in the auction algorithm and at each early step in the Sinkhorn algorithm, it's totally a thing to do. So you reach an epsilon optimal solution with max C divided by epsilon steps. Basically, a simple heuristic is to run the optimization with decreasing values of epsilon. And so that's why epsilon scaling, as it's known in operations research, it's equivalent to simulated annealing here. And in practice, as we're going to see, it looks like a multi-scale strategy. And since optimal transport is just sorting in a way, this is the equivalent of divide and conquer. It's like quicksort. It's a heuristic that's behind quicksort, but for optimal transport. And remark 3 is that optimal transport is hit very hard by the curse of dimensionality. That's very, very important. Whenever you read, especially theoretical papers, you have to keep this in mind. Because the intuition that you should have is that in low dimension, if you have distributions in low dimension, like Gaussian distributions, the distance between two samples is going to take large and small values. So if you look at your transport map, basically, you have a penalty if you don't assign point to their correct targets. So the optimal transport objective, the primal objective, it's kind of peaky with respect to the P, so to the optimal transport plan P. So if this is the assignments P, so I switch between P and pi, sorry, the assignments, and this is your objective, so the cost, so the sum of the Pij, C, X, I, Yj, the objective looks like this. And so when I say that I get an optimal solution, so a solution whose dual cost is close to the optimum up to tolerance epsilon, well, it gives you a good control on the actual transport plan. And all of these intuitions completely breaks down in high dimension. Because if you have truly high dimensional distributions, like Gaussian distributions in dimension 100, if you've never tried it, do it, the distances get closer to a constant. And that's a consequence of the central limit theorem. So it means that, yeah, actually, in your cost matrix, all points are kind of the same. So the optimal transport objective is much more flat. That's the intuition that you should have. And so having an optimal solution, it's randomish. So that, when we say that it's very easy to get nearly optimal solutions, it doesn't mean very much in high dimension. And the second thing that maybe someone's going to talk about this afternoon is that in low dimension, basically, it's easy to sample. Basically, with 100,000 samples, you have a very good approximation of your continuous underlying distribution. In high dimension, it's not true at all. Like, it's much harder to actually sample your continuous distribution. So solving your problem between these discrete samples does not tell you much about the optimal transport distance between the underlying distributions in high dimension. So that's one of the key things to remember. Now, okay, to recap 80 plus years of work, if I had to take the key dates, for discrete optimal transport with endpoints, so you have 1942, you have this thing about duality. Then in the 50s, Hungarian methods like exact algorithms, cubic algorithms. Then in the late 70s, 80s, everything about auctions. So approximate algorithms in quadratic time. Then a paper that I really like, soft to sign, Sinkhorn plus simulated annealing in quadratic time. So I think they had understood many things. And actually, this is a standard method, like using Sinkhorn with simulated annealing for 3D shape matching. It has been standard for over 20 years. You have Wikipedia pages on this. If you type point set registration, etc. So robust point matching, like CVPR papers with thousands of citations. So that's a good thing. And then, maybe 10 years ago, especially with papers by Marco Cuturi, people started to realize that basically all those algorithms are intrinsically very easy to parallelize. So they're easy to implement on GPUs. So now that we have access to GPUs, we're highly motivated to study this. So that's why you had a wave of papers, especially in the machine learning community. And at the same time, have people like Quentin Mérigot, Bruno Lévy, or Bernard Schmitzer, who had lots of insights on how you should implement things fast, especially in low-dimensional spaces with multi-scale solvers, which are kind of log linear, especially in dimension 2 and 3, which is what you expect, because in dimension 1, you should be log linear. So solution today is that really we have those multi-scale synchron algorithms on the GPU that behave like kind of generalized quicksort algorithms. I want to show them to you here. So here I have two discrete distributions. So A with the xi's and B with the yj's. Okay, and in green, so here everything is in the unit square. And in green, you have this transport plan. But in the background, you know that what really matters are those dual potentials. So functions defined on the ambient space. And okay, and the idea really, like if you do the math, is that the transport plan is given by the gradients of the dual functions in the background. Okay, and how do I get this very efficiently? Well, the thing is that you want to start with a very large value of epsilon, and the intuition is that if you have a very large value of epsilon with everything synchron related, it's as if you had only taken the low frequencies. So you start with something which is basically a translation between your two distributions, and your linear potentials are linear. And then it's going to go incredibly fast because every slide now is going to be one iteration of the algorithm. But at every iteration, I divide the square root of epsilon by 2. And okay, you do that. So now square root of epsilon is 1/2, 1/4, 1 divided by 8, etc. So I divide by 2, divide by 2, divide by 2, divide by 2. And what you see is that basically very quickly, you get this intuition that you add more and more details in your sorting algorithms. And the algorithms matches those details increasingly fast. So that's how you get very decent approximations of the Wasserstein distance in like 7 iterations. And if you want to go further, that's what we call multi-scale algorithms. You can make the first iterations on downsample versions of your distribution. So like the first 4 iterations, you do them on clustered versions of the distributions. And then when you go from fine to coarse, you know how to truncate operations that are not going to matter afterwards. And so that's how the algorithms work now. So just to be clear, the target was to scale up optimal transport to anatomical data. And the progresses of the last decade, they really add up to very significant acceleration. So if you take as baseline something like the synchron algorithm on GPU, and you implement it well on GPU, like with key-ops, you add annealing, you add multiscale, so all those things that were primarily thought in the context of physics, but that work outside of physics, with a precision of 1% on a modern gaming GPU, so something that costs like 2,000 euros or 1,000 euros, you can work with 10,000 points in 30, 50 milliseconds and 100,000 points in like a fraction of a second using these geom loss solvers that I developed during my PhD, and that now, so we are revamping it to have a nicer API, and it's already been included, but it's going to be cleaner as a backend for like the Python optimal transport library that people like to use by default, so that everyone can have access to that. And now applications very quickly, because I'm late on time. So, okay, this is a typical example of what I'm motivated by. So lung registration. I want to, basically here, I'm showing you lung images, segmented as point clouds of 4 subjects from a hospital in Harvard. And basically you have the lungs when people exhale, so that's in red, the small lungs. And then when people inhale, in blue, the large lungs. And what you'd like to get is very quickly to get this registration between those branching structures, because if you get that, then you know how people breathe, and then you're able to do statistics. Maybe when people have this kind of disease, they breathe like this, etc. And it's very typical of the challenge that we face, because we have very complex deformations. It's not linear at all. You need to work with high resolution data. Okay, this is 60,000 points. And you need to work with high accuracy, because the kind of legacy software from 20 years ago are going to do it with a very high precision. The problem is that they are going to take minutes to do it, and we want to do it really fast to enable population-wide study, these kind of things. So just if you've never read this kind of literature, if you ask someone today at NeurIPS or CVPR, what should you do? People will tell you, okay, use a point neural network, a multi-scale architecture that's going to learn descriptors from fine to coarse and then aggregate them from coarse to fine. And okay, in practice, those algorithms are very easy to train, especially on synthetic deformations. And they are extremely good at pairing branches together. You know, if you come from mathematical optimization, they're very, very good to not fall into local optima, but they are very hard to train to a high accuracy. And so, because at the end of the day, you're just training something which is basically a piecewise affine function. And for aesthetic reasons, you really want something pixel perfect. And so it's very, very complementary to what we can do with well-implemented mathematical operators, implemented mathematical optimization like optimal transport. And so I think the pragmatic method that people would use in the industry or in a medical lab is, okay, you just concatenate the different steps together. Initially, so robot, it means robust optimal transport. If you have those kind of shapes, first you do an affine registration, an affine pre-alignment, then you use your deep neural networks that you have trained on synthetic deformation. You smooth it to make sure that you don't have topological artifacts. And then to get something pixel perfect, you want to do some post-processing. And here, usually, people would use nearest neighbor projection. But if you do that, you create kind of a lot of artifacts, especially at the ends. You have many points that are going to be matched at the end of the vessels. And ta-da, we have optimal transport, which is just nearest neighbor projection plus incompressibility constraints. So it's very, very well suited to those kind of tasks. And now you can use it without killing your performance statistics. Okay, you can scale to high resolutions in a fraction of a second. So just to show you what this looks like, yeah, this is your source, this is your target. This is what they look like after a fine alignment. From the outside, it looks good, but when you superpose them together, you see, no, it's garbage. Okay, like breathing is not just a linear transformation. So that's why you use a deep neural network that's going to be very, very good at understanding that, okay, this should go there, matching the different forks together, but kind of surprisingly hard to train to pixel perfect satisfying accuracy. And now with something cheap, well understood, like an optimal transport solver, you can do that without problem. So that was really one of the main targets of this work. Second thing is that, now that we have those metrics on probability distributions, we'd like to use them to do statistics, to define Paris centers, define Fréchet means. So I don't have much time, so I'm not going to explain too much. But basically here, I'm showing you, I have 4 source distributions, B1, B2, B3, B4, and I'm showing you solutions of this argmin problem with different, with basically barycentric weights that vary bilinearly. And if the shapes are close enough with an optimal transport metric, you're going to recover kind of pleasing transport-like behavior. And from a computational perspective, okay, solving this problem with respect to the weights, it's easy. The problem is that you have to identify the support of your distributions. And this support, you just know that it lies in the convex hull of your input distributions. And there, the curves of dimensionality hits very, very hard because in high dimension, the convex hull is a very large space. So exploring it takes a lot of time. And that's why you can find papers in the literature that tell you that, yeah, Wasserstein barycenter in high dimension, it's NP hard. But for us in 2D, 3D, the convex hull, it's the same domain. So you can work with a 2D or 3D grid and everything I told you about fast algorithms work. And basically it means that today, computing optimal transport distances in barycenters between density maps, it's a solved problem, I think, as far as applications are concerned. So it's very easy to do manifold learning with UMAP in Wasserstein spaces of 2D, 3D distributions. So this afternoon, you're going to have those very nice things in the talk of Anna Song. I'm not going to spoil it, but that's exactly the kind of thing that I would like to see more later. And so basically to help this kind of research, I'm working on software to make it affordable. So conclusion, just to be clear that everything is completely teamwork, like all the software, like Benjamin and Joanna are here. So we developed the KEOPS library together. François Xavier is also there, and Gabriel is going to be here this afternoon, you know, like the theoretical results on optimal transport. Alain was my PhD advisor. Then you have Mark and Zheng Yang, with whom we did the lung registration thing, and Olga and Hugh, with whom we started to work on this manifold learning in Wasserstein space. Okay. So the key points, if you have to remember one thing, is that really optimal transport is generalized sorting. So we have super fast solvers on simple domains, 2D, 3D spaces. It's simple registration for shapes that are close to each other. And yeah, that's a fundamental, I think it's a fundamental tool. I don't want to oversell it, but it's useful at the intersection of geometry and statistics. And the main challenge for us today is, can we extend everything we did on the computational front to maybe more interesting topology-aware metrics, or, you know, physics-based metrics? That would be really the dream. And to do that, you know, there's very much an ongoing work to provide fast GPU backends for all those types of computations beyond what you have out of the box with TensorFlow and PyTorch. So if you're interested, documentation is online. Most of the figures come from my PhD thesis. That's it. Thank you very much.
We have time for quick questions in French or English. Or...
Yeah.
Yes, Sean.
I have a question about the single algorithm, which is, as I understand, more or less a fixed point algorithm. Could you additionally speed up this algorithm with some kind of accelerated single point procedure, like Anderson acceleration or something?
Yes, yes, yes. So basically, you have many, many papers written about that especially in the machine learning literature, tons of things. Personally, I think that, you know, for those types of applications, annealing just works. Mm-hmm. And, you know, basically in 8 iterations, you get something that's perfect as far as I'm concerned. So, and the intuition for that is that basically those, you know, the sync-on, you can think that you have this assignment problem. The normal assignment problem is something like that. And with sync-on, you soften it. Okay, it's a bit like if you replace an absolute value with the square root of x squared plus epsilon. And the thing is that when you optimize it with sync-on, you really have 2 regimes. Okay, the first regime is how do you get close to the optimum in the soft regime, and then once you're in the soft basin, how do you get there? And basically, I think all those optimization-based strategy, they are very, very effective there, and annealing, it's effective there. You know, and the thing is that then it's kind of a question: do we really need, like, what does it mean to optimize to numerical accuracy here? Maybe for some application in physics it makes sense. I think for everything machine learning or shape analysis related, you know, if you're close to the optimum at your precision epsilon, you should stop.
Other questions? Yes.
I'm just wondering about when you get the higher dimension and you use the epsilon optimal solution, which becomes random,
yeah.
Whether or not these solutions are related to an optimal epsilon, or is it adaptive? Because I've seen more a choice was adaptive for the epsilon rather than an optimal analytical.
Yes. So yeah, I don't know. Maybe the answer I will have is that all of this makes a lot of sense in small dimension. I mean, everything math related makes sense in small dimension, you know, the statistics, etc. And when we say we have high dimensional distributions, basically, if you say I have a high dimensional distribution and that's it, you know, basically you don't know anything about your distribution, so it's hopeless. So in all fields, people add, I have a high dimensional distribution, but I know a lot about it. So for instance, I know that it's a distribution of images, so I know that textures are important, so I know that I should use wavelets, convolutional neural networks. And then, you know, that's why the literature is kind of blooming, is that because you have, for every application scenario, you have different ideas of, you know, how do you put prior into those algorithms? And, you know, and so I think basic optimal transport, you know, it's very popular in low dimensional because the basic thing makes sense. In high dimension, I think it's more like a very useful source of inspiration. You know, it's very interesting in the machine learning literature because it's kind of one of the tractable distances between probability distributions, which does not come from a Hilbert norm. You know, so it's a very good example something that we have intuitions on and that we can leverage. Yeah, Virginie.
I've got a question about how it scales with the underlying dimension, because you showed the results in dimension 2 and dimension 3. And I was wondering, because I've in mind some examples where typically a dimension 6 would be interesting for kinetic equations, for instance, or electronic structure calculations. So it's higher than 3, but still not 300.
Yeah.
How would it typically scale the time, computing times that you?
Yes, so basically, if annealing and everything works, I would expect it to do so, but I don't want to promise you anything because it's not as though we had very strong theorems on that, and all my practical experience is with L1 or L2 cost in dimension 2, 3. So I don't want to overcommit. From the perspective of algorithms, the thing is that on a GPU, making brute force computations is very easy, and all of these so in dimension 6, basically, you're not going to be able to use a grid because it's too high dimensional to do that. And making a true multi-scale truncation, it's like a bound-set strategy. You add a lot of overhead, and it's only worth it if you have more than 1 million samples. So my advice to people is okay, if you have less than 100,000 samples, just do brute force with annealing. Probably that's the best you can do, except if you want to invest your PhD on it. And if you have more than 1 million samples, be clever. And for instance, if you know Bruno Levy, he wants to work with big simulations of the early universe with tens of millions of particles, then he wants to be clever. But below that, you don't need to do it.